Welcome back to the concluding class of the calculus of residue. So we want to integrate this such that when the singular point of this f of s is on real axis. So far we have considered the one on imaginary axis, but now we are considering the one on real axis. So let's say this is the y-axis, this imaginary part. So we integrate it along indented circle. Is minus r to r, this is a small circle here, minus small r to small r, and this is c big r, this is small r, this is called c small r, because we have considered this using Jordan's lemma. So we need to consider this too in the following theorem. Let's take the following theorem. So this is the theorem. Suppose that f of s has a simple pole on real axis, and if CR is this, divided by dz naught is this on this interval, then integral c small r f of s dz is equal to pi I times the residue of f of z inside the CR. So the proof is easy, which should be left as exercise, but if you want to get it, you can apply the well-known Lorentz series. Since it's a simple pole, we should have this z minus z plus g of z. So this g of z, this is the analytical part, and this is the principal part. Now you integrate it along this CR. Therefore, integral c small r f of z dz will be equal to a minus 1. So for this one now, this will be integral c small r dz over z minus z naught plus c small r g of z dz. So from that place, if you apply what is here, this will be equal to a minus 1, 0 to pi. Our dz, if you differentiate this will be IR exponential I theta over z minus z naught. If you bring z naught here, it will be R exponential I theta d theta plus, this is also 0 to pi, g of z. These are z naught plus R exponential I theta d theta. Okay, our dz is I R exponential I theta d theta. Sorry, this is what should be there, I R exponential I theta d theta. So this cancels this cancels this, without stressing yourself. If as r tends to 0, because of what they put here, as r tends to 0, the whole of this will be 0, because if you put r to be 0, so let's forget about it. What we have left should be a minus 1. Is only the theta that we are going to have left. There's I outside, 0 to pi. So this is simply pi I a minus 1, and the result is proved. So that will really help us in what we want to do now. Let's take example. We now take example 1. We want to show that this is equal to pi over 2. Now, as usual, we start by saying this to be 0 to infinity to be sin s over x dx, which we write as c. If this is imaginary part of exponential z, as we have known, over z, this over z, we turn it to z dz. Now, we are integrating it along an indented circle. Minus big R to big R, c big R. We indent it here at the singular point, which is 0. If you look at it, there's 0 there. This is minus small r to small r, c small r. And what is here now is that we have cut this singular point, because the singular point here, our f of z is equal to exponential I z over z. We have cut the singular point already. So in that case, z is equal to 0 does not lie inside this upper half plane again. This is half of the annulus region. So it does not lie because we have cut this 0. So by Cauchy integral theorem, the integral will be equal to 0. So let's continue like this. Now we are integrating this. This integral exponential I z over z will be integrated in this indented circle. So we have cut out the singular point there. So we integrate it from minus r to minus small r. So this will be, without stressing myself, sin s over s ds plus this second one, this is the next one, this arc small r, that is exponential I z over z dz. That's what we are using for that, plus small r to big R. This is sin s over x dx. And finally, see this big arc here. This is exponential I z over z. You will see that I did not use exponential I z here. It's because we have said that imaginary part of I z is sin s already. All these are imaginary part. Or let me put it further. Imaginary part. Imaginary part. This will be 0 by Cauchy integral theorem. This will be 0 because here z is equal to 0 does not lie inside this integral again, but we still need the residue. Let's find the residue. Residue as that z is equal to 0 becomes z tends to 0 exponential I z over z times z. So this cancels this. This is exponential 0 and that is 1. So we need it. We are coming there. Now let us now come back to this place. The first integral is 0. We write it there. Why is it 0? Because in this place, z is equal to 0 does not lie in this plane. So by Cauchy integral theorem, this function does not have any singular point there. So the integration with respect to z will be equal to 0. This one, I'll tend r to be infinity, and small r, I'll tend it to 0. This is it will be minus infinity to 0 sin s over x ds plus, now for this c bigger, I will use the theorem that I just proved. So remember, we prove it to be plus pi I. So this one now is moving from pi to 0 instead of 0 to pi. So it will be minus pi I times the residue. That is what we proved the other time, times the residue. The residue here that we got is 1 plus, for this one, this will be 0 to infinity sin s over x ds plus this last one. This is Jordan's lemma. This is 0. We have proved the Jordan's lemma. So this is 0. So let's bring the whole of this to this place. This one will bring it here so that we have pi I equal to minus infinity. We can match these two together. Minus infinity to 0, 0 to infinity. That is minus infinity to infinity sin s over x dx. Remember, we are using the imaginary part. We have said it is in of that function. So without stressing myself, I don't need the I again because it is imaginary that we are considering. So this simply shows that minus infinity to infinity sin s over s ds is equal to pi. So since it's equal to pi, we cannot say, and this thing is even function. This is odd and this is odd. Odd divided by odd will give me even. So this will be 0 to infinity sin s over s ds, which is equal to pi. And finally, 0 to infinity sin s over s is equal to pi over 2. So that proves the result. And also we can proceed here by using exponential ix. Exponential ix. If assuming that is what I want to use, I will have got the following. This will be 0 equal to minus infinity to infinity exponential ix over x dx. Now minus pi I, which should be pi I equal to minus infinity to infinity exponential s over x. So this can be written as, we know that exponential is the same thing as cos s plus I sin x divided by x, which I can split to be minus infinity to infinity cos s over s ds plus I minus infinity to infinity sin s over x ds. This is pi I. When we compare both sides, you see that the real part has no, or you can say that 0 plus pi I. We compare real part to real part, imaginary part to imaginary part. So that simply shows that minus pi to pi cos s over s ds will be 0 if you had found it. And minus this to this, sin s over s ds, that will be equal to pi. That is from this one. So we have used the two methods to prove it. Let's take another example. So we want to evaluate this integral as well. Now, let us first take note of the function of z there. This is iz over z into 1 plus z squared. So z is equal to 0, z is equal to I, z is equal to minus I. They are the singular points here. In the upper half plate, this one lies, but this one lies on the real axis. So this is what we are going to do. We integrate it in an indented circle because we have this there. Let's cut the 0 that is there. This is the 0 minus r to r, big R minus big R, c small r, and c big R. In fact, this, let's say this place is I. Z is equal to I. So we can now write this in terms of f of z. So this will be imaginary part of exponential iz over z into 1 plus z squared dz. Now we integrate it along this. So along this we have minus big R to minus small r, imaginary part of exponential ix over s into 1 plus s squared dx, plus this one is c small r, imaginary part of exponential iz over, or let's just put exponential, let's forget about the imagine, let's just use exponential iz. So we have known that sine is imaginary, so let's put exponential there, ordinary exponential. Also this is z over 1 plus z squared dz. It remains this one, r to big R. This is exponential s over s into 1 plus s squared ds. And finally the big R, c big R, exponential iz over z into 1 plus z squared dz. Without stressing myself, we should know that this one is 0. In the other question, we see that the function has only 0 as a singularity, and at the end of the day we later result to 0 because we have indented the circle of that 0, so we remove it away, so it has no singular point again. But here now, even when we indented this circle here, we still have a singular point here, which is I. So in that case, this one will be, if you integrate this, it will be 2 pi I times the residue at that point. This is the only residue, this is the only singular point there. So I will need to find 2 residues now. Residue at z is equal to 0 first. So this is limit of z tends to 0, z times this f of z. So this cancels this. So put z to be 0. This is exponential 0 over 1 plus 0, and that is 1. So we keep it. Also, residue at z is equal to I. That will be a minus 1, or let's say b minus 1 is equal to limit of z tends to 1, I, z minus I times f of z. This is our f of z, exponential iz over z times, remember this one can be written as z minus I and z plus I, so that this will cancel this. Anywhere we see z now, we put it as I. This is to just be exponential I times I divided by I into I plus I. This is exponential minus 1 because of that I squared over I times I. This is minus 2 because this is 2I. 2I times I is minus 2. So we have found the... Now let's now integrate all this. 1, 2, 3, 4, 5. For this one, what we have is 2 pi I times the residue. This is the only residue there. Exponential minus 1 over minus 2. It will be equal to minus infinity to 0. That is, as usual, we turn big arc to infinity, we turn that small arc to 0. This is exponential ix over s into 1 plus s squared. This will give me minus pi I, if you use the theorem, times the residue. The residue has been given to us here as 1. We have found it here. Residue at z is equal to 0. We have found it. Plus the second one, 0 to infinity, this one. Put r to 0, big R to infinity. Exponential is over s into 1 plus s squared ds plus 0. This one is 0 by Jordan's lemma. So continue from that. So this will be equal to 2 cancel 2 there. So we have minus pi I exponential minus 1. When you bring this minus pi I, it will become plus pi I equal to, we can merge these two together to become minus infinity to infinity exponential is over s into 1 plus s squared dx. Pi I is common. So this is 1 minus exponential minus 1 is equal to, remember, this is cos s plus I sine x, both over s into 1 plus s squared dx. So if I compare the real part, there's no real part here, which is 0. If you compare, you should have minus this. This is cos s over s into 1 plus s squared ds. There's no real part, so that one is 0. And for the imaginary part, this is sin s over s into 1 plus s squared dx. That one is equal to pi. We don't need the I again. Pi into 1 minus exponential minus 1. So that is the answer. That is the solution to the given question. Is the given question.